Welcome to our course on Programming 2, and I know it's a bit challenging today, now in between the holiday and the weekend and the nice weather, so I'm glad to see that some of you made it to come to the lecture, and I'm also very happy that I may announce Oscar Nierstrasz as our guest lecturer today. So I think now it makes sense to also introduce you a little bit, because the previous generations have also have known Oscar, but you're a bit younger. So Oscar has been actually my predecessor here at the Institute of Computer Science and was doing research on software engineering and programming languages for 25 years or so, right? Until the end of 2021. Officially he is retired, but still actively doing research, maybe not in the same frequency anymore, but still interested in all ongoings and also contributing to new ideas on object-oriented programming. So Oscar is really an expert in object-oriented programming. And so I'm very happy that he still delivers some of this experience and some of these insights and valuable contributions with us in terms of this course here. And the guest lecture today is dedicated to a bit of Smalltalk programming. So you will see that Smalltalk is another object-oriented language, much more pure in terms of object orientation than Java, also with a little bit of a different syntax, I would say. But today it's not so much about Smalltalk and syntax of Smalltalk, but it's more, I would say, about this paradigm of live programming, something that we do not have basically in Java, except you're running a Java program inside the debugger. Then you have a bit of this feeling of doing live programming, but it's not I would say, a native concept of Java as a programming environment. And yeah, with that, I think Oscar can explain you this much better than I can, and I'm very happy to hand over to you, Oscar, for today's guest lecture.
Thanks very much, Timo. Okay, so as Timo mentioned, I'm going to show you a little bit about the Smalltalk programming language. Has anybody heard of it before? A couple of people. So it's been around for a while. It's a little bit of an oddball language. It has a curious syntax, but very, very simple one. You can learn the syntax, as we'll see in a few minutes, of the language. But what's special about it is that you have a different style of programming and development than you do in most conventional languages. So it's really a live programming system. You don't, so normally when you program in a language like pick your favorite language, Java, Python, C++, JavaScript, whatever. You're in an environment where typically you write a program in a text editor, you then compile it or pass it on to, it's compiled to some bytecode or to machine code, and then you run it with a virtual machine or you run it on the bare metal. And then you discover problems and bugs, and then you go back and edit your code again, and you're in this life cycle. Whereas in a live programming environment, you're actually, the program is always running. So you're always in a running system. And what you do is you make small incremental changes. So these changes are modifying a method or creating a class. And each of these deltas is a very small thing. So I'm going to show this to you and use as a running example the project that you developed in Java during P2, which is the Ludo game. So there are going to be two parts to my talk. First part, I'm going to give you just a basic introduction to Smalltalk, and in the second part, we're going to dive into more of the development tools and environment and how this changes your perspective of software development. So as an appetizer here, we have a Ludo game. If you think about a classical application, there are two things you can do with it. You can look at the source code, or you can run it. So here we have the actual running game. I can actually click here and wait until I get a 6, and then eventually I 6, so now player B can move, and I can get player B into the game, and I can continue playing here. So I have this view of my software system, or I can look at the source code, and I'm sitting there in a text editor, and I'm looking at all of the different classes and methods and packages and so on. So what I would argue is that this is a very poor way of understanding software. You either have the running software or you have source code, and there's a huge gap in between. So what I want to convince you of, and it'll take me some time because I want to first introduce Smalltalk, is that there's another way. And that's actually, so I'm here, as Timo said, I'm retired, but I'm actually working for a former student of mine who has a very interesting startup called Fink. And they've developed a platform called the Glamorous Toolkit. So it's a Smalltalk environment that supports what we call moldable development. You can actually download that yourself if you want. By the way, from the course webpage, you'll find a link. And there on the link, you'll find a description of the program. There's a link here for downloading Glamorous Toolkit. And there's also a link to the annotated slides. So this is just a static web page with the slides and some text description. So it's kind of like a transcript of what I'm saying. But what's far more interesting is you can actually download Glamorous Toolkit and run all this stuff yourself in the environment. So it's open source and available for Linux, Windows, and Mac. Okay, so we're going to get to the point where I'm going to show you that working with the Ludo game can be a different experience than what you've had so far in a live environment. But let's start first with some basics. So what's Smalltalk? And the Smalltalk basics, showing you a little bit of the syntax, and then we'll have a look at what live programming is like with Smalltalk and with Glamorous Toolkit. We'll see that there's a slightly different approach to testing, where tests not only where they're not just unit tests, but a unit test will also return an object for you. And this becomes very powerful. So it's just like a unit test as you know it, but the one small difference is that every test returns an example object, and this is very powerful. We'll also have something which might remind you of Jupyter notebooks. We call them Lepeter. And they're a step beyond Jupyter. You can have live examples and code within the Lepeter notebooks, and you actually have a kind of a knowledge base of information about your software projects. And then I'll slowly wrap up. So what is Smalltalk, and where did it come from? Object-oriented programming has been around for a very long time. It was invented in the very early 1960s. So in 1962, a couple of fellows in Norway, Ole Johan Dahl and Christer Nygaard, they were building simulation applications using a language called Algol at the time. And they discovered there's a huge abstraction gap between the things that they wanted to model and the low-level programming language. And they said, gee, it would be cool if we could represent these real-world objects in our code itself. So what would be nice if we had classes of objects, and these classes maybe even inherit from each other, so we can model a conceptual hierarchy of objects. So they invented an extension to Algol, and they called the language Simula, and after some years, when it was implemented and they really started building a community, they discovered, hey, this object-oriented programming stuff, it's not just good for writing simulations, but any application can be thought of as a simulation. When you program anything, you're building a virtual world with objects. And said, oh, object-oriented programming is not just for simulation, it's a more general paradigm. In the 1960s, a fellow in the United States by the name of Alan Kay, he ran into this and thought it was super interesting. And he also noticed that computers were getting faster and smaller. And he said, heck, if I extrapolate, maybe 10, 15 years down the line, computers will be small enough that you can actually hold one in your hand. And he invented this idea. He called it codenamed Dynabook. This is a mock-up from the 1960s. It didn't really exist. And he said you could have a Dynabook as a computer you can hold in your hand with multimedia graphics and all sorts of knowledge and interconnected pages about all sorts of information. And he said, we can't build this now, but pretty soon we will. So he convinced the Xerox company at the Palo Alto Research Center to fund his project for something like 10 years, from starting around 1970 to 1980. And he said, you know, if we're going to build these things from the ground up, we're going to build not just the software and the operating system, but the hardware too, it's going to have to be object-oriented. So he was convinced by Nygaard and Dahl, and he said, they're onto something. Programming in this low-level way won't work. We really need to represent and have conceptually all the way down to the lowest level the notion of objects. And that's when Smalltalk was invented. So starting in 1972 was the first time they had the first prototype of a language, and it took them many years, took them 7 or 8 years or more before they finally developed the version called Smalltalk 80 now. They developed their own hardware, so that's an Alto computer workstation. Workstations didn't exist before then. I mean, the first prototypes were in the late 60s, but they really invented that. And they invented the whole notion of a graphical workstation with a graphical windowing system using a mouse and windows and so on. So that all came out from Xerox PARC at that time. And the first implementations were in the Smalltalk language. So that's where that originally came from. What I'm using now is a descendant of that Smalltalk 80 system. Many years later, in the 90s, Alan Kay worked for Disney and later for Apple, and they took their Smalltalk 80 and they invented a new multimedia version of it called Squeak. Squeak eventually forked and became another version called Faro, which is an open source software, and Glamorous Toolkit is built on top of Faro with its own live windowing system. The idea of Glamorous Toolkit is that you have a moldable development environment. And I just want to give you a little hint of what that means in my talk today. So the idea with moldable programming or moldable development is that instead of having completely generic tools in your development environment, while you're developing, the tools become adapted to your domain. So if I'm modeling the Ludo game, I don't just want to see generic views of my application. I'd like to adapt it so that the tools know about my Ludo domain, and we can see these objects in the environment in a domain-specific way. That'll become clearer later on. But that's what that's about. The idea is I want to mold the development environment so it knows about my software. That's different from the way development environments work today. So I'm going to show you what that looks like. It's also a platform for software and data analysis. We've been using it in some research projects, also with some of Timo's students. And GT is built on top of this open source Faro. So Faro is open source and downloadable. You can also separately get Glamorous Toolkit, which has its own windowing system and environment built on top of Faro. So here, for example, this is the Glamorous Toolkit desktop here running inside a slideshow. So it comes with a whole knowledge base inside the environment. So these are the Leopard notebook pages, and we'll see some of those in a few minutes. It's useful to understand that it's a live development, live programming system. Smalltalk is live. What does that mean concretely? How does that work technically? Because normally, you write code in a text editor, you pass it to a compiler, and whatever is compiled, you run it on a machine, or you pass it to a virtual machine, and then you see the results. But there's a huge gap between writing the code and actually seeing it running. In Smalltalk, all Smalltalk implementations, or nearly all of them, work the following way. You have 4 pieces. We don't have a pointer here, do we? Oh, I have a mouse. Keep forgetting that. So basically, you have one thing called an image. So this slideshow is running inside the image. So the image is just a huge address space, where all the objects live. That image can get saved to a file, or like a snapshot, and then loaded back up again. So if I quit the system now, and then start it up again, I'll be back to where I was at this moment. This is running on top of a virtual machine here. So the virtual machine is just like a Java virtual machine or a JavaScript virtual machine or whatever. That's kind of standard. But what's different is when I program, I'm in this environment. And what I make are small changes to the environment. So these are these little deltas you see here. Also, the entire source code of the current version of the system is also available. So I can also see the source code of anything at the system at any time. And I can make changes to that as well. So the part at the bottom is generic. That's the snapshot of the system, the Smalltalk implementation, whatever version you have with its source code. And then you, everybody who's programming, everybody has their own copy of an image. They do their work in there, and the changes get filed out as well. And every time I make a change, the changes are also synced to the file system so they can't get lost. So you can deliver an application where this is missing, or even that the code is obfuscated. Normally, applications are open source, but the customers we work for, their code that they need for their company, that's not open source. So Glamorous Toolkit is open source. We work with a company called Lifeware that does life insurance support for life insurance companies. They provide persistence support and database support, and they're using our platform. Their code is not open source. That belongs to them. So yeah, you can have open source or closed source. We wanted to make sure that people could use our system, so we have, I'd say 99% of our code is open source. There's some things that we developed for customers that's not in there, but basically if you want to use it, you're free to do so. There are also tools here. So when we develop, we don't just save things in files. We are using, usually programming, developing with GitHub. So everything is synchronized. All the code is synchronized to GitHub repositories, and we use continuous integration to make sure that all the tests are run and the whole system is, that nothing is broken when there are changes over time. And if there are, they're fixed as soon as possible. So on top of this kind of basic view of the system, you can have all sorts of more modern kinds of tools. Typically, when I'm programming, I start from a notebook page. And suppose I want, let's just have a hello world program. So I'd like to have hello, which is a class. And I'd like to create a new instance of that. And I would like to send it the message, hi. And that's supposed to return the string hello world. Okay? That class doesn't exist. Can you see it clearly, or should I zoom in? It's good? Okay, so what I would do is I would say, I want to create this class. So it's a fix-it. And here I get a template for that class. I should give it a package name. I'll call the package demo. Demo. And I create it. And now the class exists. So I could evaluate hello new. Oops. Excuse me, I always have this problem with the mouse and the laptop while I'm standing here. Here I have now an instance of hello. So it's in the running environment. The method hi doesn't exist. So if I try and evaluate this, I'll get a debugger error saying it doesn't understand hi. It's not there. It's not implemented. I could work here in the debugger, or I could just do another fix-it here and say, oh, let's create this method, and this method hi, and it should return the string hello world. And now it's yellow here, so I compile it. And now I've created a class and I've created a method. And notice I have a code bubble, so I can at any point zoom in to a class or to, and now if I evaluate this, I get the result back, which is hello world. I never left the system. So now in the system, there's a new class called hello and a new method of that class called hi. And here's a view in the coder. And if I open it up this way, I can see these are all the classes in the system and the packages. And there's a new package called demo and a class called hello. And I could also delete this in the system right now. So it's gone. And if I go back to where it was before, now this code will be broken again. So I just added a class and a method, and I deleted them again. So while the system was running. I could also do the following. So let me see. We created this guy, class hello and demo. And I try and run this code, and I'm in the debugger, and it's not working. Well, I could, inside the debugger, create the method hi, say, hi there, and compile it, and continue executing. Oh, and that should have worked, but I don't know what went wrong. Anyway, within the debugger, I can make changes while I'm on the runtime stack, change the running code of the classes involved, and continue executing. So those are all things you can do. Okay, so what's important here? Everything is an object. So the hello instance is an object. Actually, the class hello is also an object because I can inspect it. And everything happens by sending messages. So here I could actually inspect this guy. And now I have an inspector on the hello class. So it has a definition, and it has methods, and it has instance slots, and so on. So here I can see what is a class and what are the parts of its implementation. So I don't just have an object. So if I say hello new, that's a different thing. That's an instance of the object itself. And it actually doesn't have any state. It's just printing, it just is an object without any instance variables. But the class is a much more complicated thing. Furthermore, even a method is an object. So if I inspect the method, well, it's a compiled method. And here's the source code. Here's the byte code. Here's the intermediate representation. And I can even look at the abstract syntax tree of the source code. Now, notice something here. If you normally inspect objects in your favorite Java IDE, you will see just one thing. You will see probably this view, the raw view. It just shows me the contents of the object. What we've done here is we know that a compiled method is a special kind of object, and there are interesting things about it. So we've molded it. We've given it additional views. So I say, well, a compiled method, I'd like to know what its source code is. I'd like to know what its Git history is and how many versions of it were over time. In fact, we created a couple of versions of this while we were working. Yeah, there was an earlier version. Oh, but we deleted that from the system. But yeah, and there are other things, like a syntax explanation is another kind of view you might like to have. So what we've done is we've said for the system itself, we'd like to have dedicated views which explain these objects to us. And this is the part of the molding. Instead of getting completely generic development tools, you augment the tools so the tools know about your domain objects. And we'll see that later with the Ludo game as well. Good. Everything's an object. Classes are also objects. Methods are also objects. Everything happens by sending messages. So everything that we did, even when we were clicking through the user interface, somewhere down there a message was being sent to some object. The tools in the environment are objects as well. Everything is made up from objects, down to the lowest level. I will move ahead. So, as examples, numbers are objects. So 1 is an instance of a small integer, and it's actually an instance of the small integer class. Notice small integers also have some views, and these are just views for numbers. For example, one thing interesting to know about numbers is how would I represent it as decimal or hex or whatever. So that's a nice view to have. That would be useful. So it's been added to the system. If you normally inspect a number in Java, in the Java debugger, you will only get one very simple view. A string is in single quotes. This is a gotcha, because everybody expects you to use double quotes. Double quotes are comments in Smalltalk. So that's a slight difference. But if I inspect this guy, I see the string view. I can also see the live view. I can also dive into it and see that a string is made up of a sequence of characters. So the $sign is Smalltalk syntax for a character. So this is $H and $E. And now I can dive in further and see, well, this is an instance of a character. And I can see its class. So even a character, even a lowly character, is a real live object with its full implementation. And I can see all the source code in the system of all of these the complete behavior of the character. It's all there. Because this is the version of Smalltalk where I have all the source code available. Booleans. You'd think a Boolean is too low level. Here's a Boolean. Here's the actual object. Here's the raw view. It's not very interesting. But we can look at the complete implementation. And we can see that true is an instance of the class capital true. And in fact, if we look at the class hierarchy, we see that the class true and the class false are subclasses of the class Boolean. And they are subclasses of the class object. They're really, really objects. Of course, there's some magic going on. So the implementation, in order to be fast enough, when you compile the code, it's really, when you're working with Booleans, it's working at the level of the virtual machine. If you try and change the class true or false, they're so low level that you may run into problems. But if I want to add methods to the implementation of the class true, I can do that. I can make such changes to the system. Here's a little bit of syntax which is different. In square brackets, that's a block. So that's just a lambda. It's an anonymous function. In this case, there are no arguments. And to evaluate it, you just send value to it. And if you want arguments, then I can just say colon x, x plus 4, and now I have a block with an argument. And then I would have to provide the argument when I evaluate it. So here, this is a function without a name that takes an x and adds 4 to it. And if I evaluate it with argument 5, then I'll get 9 back. So that's kind of basic syntax of Smalltalk. There are just a few more things, and then you've learned everything there is to know about Smalltalk syntax. Classes are objects. So I can send a small integer as a class, but it's an object too, and it has what's the equivalent. So if I look at the interface of this guy, of this class, I will see methods that are instance methods and some are class methods. This is like in Java when you have static methods. So there are methods that are for the objects, the regular methods, and then there are ones that are static. So you don't send those messages to, you don't invoke them on the objects, but you directly send it to the class. It's more or less the same here. So there is a maxval method here, and it will tell me what's the maximum value of a small integer. So I don't say small integer new maxval, I just say small integer maxval. And that's the biggest small integer that I can have. Now here's a puzzle for you. What will happen if I add 1 to the largest possible small integer? What would you expect to happen? I'm going to get a glass of water. Yes?
The conventional answer would be an overflow. So
Good.
Negative if it's signed.
Anybody else have a different opinion? Yes?
I would also think overflow, but maybe you made some precautions that you changed to the next bigger integer type.
Yeah. So small integers are represented directly in the memory that's available. An object is a pointer. So once upon a time it had 32 bits. Now, since we have bigger machines, there's 64 bits. But basic idea is that a small integer is using these 32 bits. But that can also be a pointer to the state of a complex object with all of its fields. If we add 1, we get a new kind of object, which is a large positive integer. So it's actually a pointer to a more complex state. Now I can talk to this guy. So here I can open up a little playground and talk to this object. So what would you expect to get if I subtract 1 from this large positive integer? Well, no big surprises. We get a thing that's smaller, but notice the type. It's no longer a large positive integer. It's smart enough to realize, oh, now I should convert myself to a small integer. And you can have very, very big numbers. So let me see. We have factorial of, we can have 50 factorial, we can have 100 factorial. These are very, very big guys. with lots of space here. So if I want to really see, I can probably do 1,000 factorial. And notice it's pretty fast. So we can handle really, really big numbers without having to tell the system, hey, make this a big number, make this a small number, like we have to do in Java. So Java, you either get an overflow or you have to explicitly convert things. You don't need to do that here. Methods are object. We saw that a moment ago. So I can ask for, is it even? It'll say yes. And this method is a method implemented in the small integer class here. Here we can see the code of it. But to access it, I can just send a message to small integer, to the class, and say, hey, give me the method with the name even. So that's the greater than notation. This is look up the method in my class. And here we have the compiled method. We saw this a few minutes ago. And it's got a whole bunch of views. We can see the bytecode of asking a number if it's even. And you can see it's a stack machine. So it pushes the number and pushes a constant. It does a bit and with, so basically if you want to know if a number is even, you look at the last bit. So we do a bit and with 1, so that just extracts the last bit. And then we push a constant 0 and send equals, and we ask, is the last bit equal to 0? If it is, then we're even, otherwise we're not. So you can actually see the low-level bytecode implementation of this method. Okay, and you can even send messages to the compiled method and say, well, what's your source code? And we'll even reconstruct that. So everything's an object, and everything happens by sending messages. But this really, really goes deeply. So this is a page, a Lepidor page, that I've created dynamically. It's sitting inside the slideshow. And this page has snippets in it. And this snippet is a code snippet here. And I can inspect the snippet, or I can send the message page to it and say, hey, snippet, give me your page. And if I inspect that, well, this is that page being inspected. So it's literally the same object. It's just that this is the user interface of the object. If I click here, I will get the inspector view instead. So that's what we're seeing here, the inspector view with all of the different molded views. So I can have a view that shows me all of the snippets. So it's a hierarchy of things. I can see all of the incoming links or the outgoing links. Or I could go to the database of this guy, inspect the page's database. I can see all of the pages in the database there. So this is quite cool. The Ludo game is an object. I just send the message new to Ludo game, and now I'm inspecting the Ludo game. We'll get back to that in a few minutes. Let me leave that one alone for the moment. Tools are objects too. So if I want a text editor or coder, the IDE tool for the small integer class, I can just open that here. And now I can get the view of the whole IDE from the tool. But it's just an object. The slideshow is an object. Different ways of doing that. So here's the slideshow itself. And I can have a look at all of the slides in here. And the slides themselves are also objects, and they have source code, which I can dive into. And even the environment is an object. So here I've spawned a new instance of the Glamorous Toolkit environment, which is sitting inside a slideshow. This is one of the things why we had to create our own windowing system, because if you have classical kind of windowing system, things at the level of tools and at the level of windows and at the level of individual characters or fonts, they're different kinds of entities and you can't mix them. So we have a view that everything has a single rendering tree. So you can take any object and embed it inside any other object. So that's why we can do this. That's hard to do in other environments. Let me just check the time. Good. Everything happens by sending messages, everything literally. So why do I talk about messages? When you were learning Java or whatever programming language, you probably heard people say, oh, you invoke this method, or you run this method. The word method comes from the Smalltalk project in the 1980s. This is terminology invented by Alan Kay and his team. They had this model. They said, with Smalltalk, we want a world of objects, and the objects communicate with each other by sending messages. I send you a message saying, could you please do this? And then I, as an object, you as an object, say, that's an interesting message. I wonder, do I already have a method for handling that message? That's where the word method comes from. A method is how you do something. I send you a message. I don't tell you what method to use. If Timo asks me to prepare a guest lecture, he doesn't tell me how to do it. He just says, prepare a guest lecture. That's the message I get. And I think, do I know how to prepare a guest lecture? Yeah, I have methods for doing that. That's my business. He doesn't tell me what method to use. He just sends me the message. So the paradigm is extremely important. It's been completely forgotten and abused. So you never hear about message sending anymore. The reason is that message sending is a little bit unfortunate as a paradigm, because then you think of concurrent systems, agents sending messages to each other. And that's probably why the terminology got forgotten. But that's the origin. But when we were working in Smalltalk, we go back and we actually use this terminology because it's the only way we can keep straight what's happening. So message is a request for service. The method is the code you use to fulfill the request. If I write 3 plus 4, let me just increase this a little bit. I'm sending the message plus to the object 3. So here's the object 3. Here's the message plus. This is what I send it. And it has an implementation, which is the method. The message consists of the plus and the 4. So that's the whole thing together. And when I evaluate it, the object 3 gets the message plus 4. It finds its method, evaluates it, and gives back the result. That's what that means. Now you know it. Just keep it in mind. That's all there is to it, really. Everything that happens by sending messages. Everything that happens that's arithmetic as well, all computations are message sends. So 3 divided by 4, that is going to give me a fraction object. How do I get the fraction object? Well, this is just a factory method. The divided by is actually going to do some work and actually at some point create a fraction object with myself as a numerator and the other number as the denominator. That's what's going on here. So it's just a factory method, super simple. Here, if I have 3 equals 4 not, well, 3 equals 4 is a Boolean object, and I'm sending the message not to it. So then instead of a false object, I get a true object. And we saw blocks already. This is just a message send. Everything is happening by sending messages. Object creation is a message send that's sending a message to a class. A class is also an object. Here I get a new ordered collection with nothing in it. Here I'm creating a fraction manually by talking to the fraction class. And numerator denominator is simply a message of the fraction class. Notice here, this is a class method, not an instance method. And here I create a set with 3 and 4 in it. And there's other nice syntax for creating sets as well. But when you change the system, you are also sending messages. So if I want to create a new class called my class, I do that by sending the message subclass to the class object. And if I want to compile a method before I use the user interface, but I can simply compile. I can say, my class, please compile foo return 42. And now I can create an instance of my class and send it the message foo, and I'll get 42 back. So all of these changes to the system were done within the system by just sending messages. So everything you do by interacting, you can also do by programmatically by sending messages. I can also remove this class by asking Smalltalk, hey, get rid of this class. And now, notice immediately this was updated, so now this code is broken and I see the wrenches here. So it's no longer valid. You can change almost anything in the system. So Smalltalk is designed so you really can change stuff. So if I remove the class called object, that should destroy the system because now the hierarchy doesn't have a root anymore. Luckily, that's one of the few changes that you're not allowed to make. If the system will complain and say, hey, you better not remove object because really everything depends on it. So we won't do that. But you can do all sorts of things to break the system. Is that good or is it bad? Well, you'd like to have a system that's completely safe, but if it's completely safe, it would probably forbid you from doing things that sometimes you might like to do. So instead, the design in objects in Smalltalk says, you can change anything in the system, but if you do something stupid, it's your risk. So buyer beware. And that's why it's important we have this design with the image and the changes. If you're programming and making changes to the system and suddenly you do something that causes the system to stop or halt or crash, you still have the code that you changed and you can load that again and be back where you started. So you don't lose your changes. Let me see. I'm going to quickly get through the last, so I'll take a few more minutes to get at least through the introduction to Smalltalk before, and then after the break we'll dive into what we can do with it with Ludo. We've seen a bunch of syntax, but I didn't explain it explicitly. There are 3 kinds of syntax for sending messages. You can send a unary message, so I send factorial to 5, whereas in Java, I would write something like number 5 dot factorial, something like that. You know, you'd have to use the dot notation. You always have to have the parentheses and so on. So that's not necessary. So it's a much more lightweight. I can send unary messages to objects or to classes. So here, float pi is going to give me the constant pi, and that's just a class method. Or Ludo game new sends the message new to the Ludo game class. These are all unary messages. Then we have binary methods like messages like 3 plus 4, or comma here is used to concatenate strings. So hello, comma, space, comma there gives us hello there as a string. Or less than, that's going to do a bit shift. So that's the bit 1 shifted left 10 times is 1024. So you can use a large range of different symbols for building your own binary messages. In Java, that's not allowed. In Python or C++, you can overload, you can have binary messages as well, but not in Java. And then the last one, which is a little bit odd, is keyword messages. So in Java, I would write something like this, probably. 3.raised to modulo, and then I'd have, 10 and 5, like that. I'd have to use this kind of a syntax. Whereas instead, you can split up for each argument, you have a different keyword. Has anybody seen something like that in another language? In Python? In Python, you can do something similar. So you can have these keyword style messages. So here, a Ludo game, I can send it the message roll with an argument. So every time I have arguments, I have a keyword, double colon, argument. If I have more arguments, add more and more keywords. So that's a single message send with 2 arguments. And I think the last one, I'm getting close to the end of the time for the break. What's the precedence? Super simple in Smalltalk. First unary, then binary, then keyword. So if I write 2 raised to 1 plus 3 factorial, the 3 factorial gets done first, then the 1 plus, and finally the raised 2. Which means that if I evaluate this, 1 plus 2 times 3, it is not 7, but it's 9. And that's almost never a problem. If you don't like it, you just add the parentheses to get what you want. So it's not like most languages where you have, like in C++, there are at least 10 different levels of precedence. Here, there's just 3. Oh, a couple of more things. You have radix numbers. So this is a binary number. So the radix 2. And this is a hex number, radix 16, 2A, that's also 42. Very rarely use those. We've seen characters, we've seen strings, you've seen comments, but I didn't emphasize them. So there's no object here. So if I evaluate that, I get the nil object. So a comment is not an object. It's one of the few things that isn't. But classes have comments, so I can ask the Ludo game, what's your class comment? That's the comment you find in the source code. And then there are symbols. A symbol is just like a string, except it's unique in the system. So I can have two instances of hello world. They're separate strings. But this guy, there is only one of me. There's only one in the whole system. So it's guaranteed. So that's very useful if you want to build a symbol table or a dictionary or something. And there... two kinds of equality. This is asking, are these the same identical object? And this one is saying, are they the same value? So this is also true in all object-oriented languages. You have the distinction between object identity, is this the identical object, or object equality, different objects with the same value. Just like in Java, you have equals and also dot equals. So it's the same difference. One is testing, are these objects the same object, and the other one is, do they have the same value? And these guys are built-in constants. There are very few keywords. Nil is one of them. False and true are two more. And we have syntax for arrays. So this is a literal array with the hash. So that's going to build me an array consisting of the number 1, the character A, foo, and a nested array of I am nested. This is a compile time object, whereas with the curly braces, that's dynamic. In most cases, you don't care about the difference, but here this is dynamically computed. So here it's the array with 6 times 7, that's computed, whereas there's nothing computed. And then the second component is this fixed array. So that's how we can create dynamic arrays and other kinds of collections. Blocks we saw, blocks with no argument, block with 1 argument, block with 2 arguments, blocks, and then you can do funky things like pass blocks as values. I'll skip over that, but here basically all I'm doing is I'm taking a block as a value, passing it into another block and composing them. But that's not important for what we need to see later on. Finally, there's self and super. These are pseudo variables. They refer to the object itself. And what's important to understand in all object-oriented single inheritance languages, there's a notion of super, and there's a difference between self and super. So in Java, it's called this, but the difference is exactly the same. The only thing that changes between self and super is that you look up methods in a different way. So with super, you start searching in the superclass, and in self, you start searching in the class itself. But the objects are the same. Self and super are the same object. Good. Finally, this is just a little bit of resuming the syntax highlighting. We have unary, binary, and keyword messages. We have temporary. Here we have a method. The method is called compute target for a token. Here we have definition of some temporary variables within the method. The rest of the code we've seen before. A period is used to separate statements, not a semicolon. So it looks more like sentences in a language. And we have self here. We have integers, and return is, we've seen it a couple of times, is the caret. So there's no return keyword, instead it's a symbol. So the caret symbol means I'm returning at that point. I can do an early return or usually return at the end of the method. And then there are a couple of other things I won't go into. Oh, we have assignments, and we also have cascades, but we might see them later. Good, so that was a super fast overview of the syntax of Smalltalk and some of the basic concepts. There's not much there, that was basically it. but we'll see after the break what we can do with this. And we'll dive then more deeply into the Ludo game. Okay, let's start at 20 past. Good. And if anybody wants to chat or ask questions, I'm available in the break too. Okay, now that's on. And it's not muted. Good. Okay, so we're back. Oh, now I hear myself through the speaker system. So we had some of the basics. We saw everything's an object in Smalltalk, and everything happens by sending messages. And I told you a little bit about the idea that Glamorous Toolkit is a special Smalltalk environment where the IDE tools are moldable, and we saw a couple of examples of that. At the very simplest level, that means that the object inspector should be moldable, which means that when you're inspecting an object, you can have not just the plain old raw view, but you can introduce other views of these objects. But you can also add special actions to these views. You can also add special queries, searching, and there are other tools that you can mold as well, such as the debugger. But I'll stick mainly to the object inspector views because these are some of the most useful ones and the easiest to understand. So here, if we have an instance of a Ludo game, here's an embedded Ludo game embedded in the notebook page, but here I'm inspecting an instance. So what I see in the left here, that's a Lepiter page, so a notebook page, containing text and code snippets and embedded examples and other kinds of things. I can inspect that too by clicking here, and now I have an inspector view of the same thing, which is showing me all sorts of other things. Here I'm inspecting the Ludo game, and it has different views here. So at the basis, every object gets for free the raw view, the print view, which is like toString in Java, and the meta view, which is like the text editor view of the class. So these you get for free. The other views are ones that you add. So I added a view, say, okay, I've developed a user interface for the Ludo game. I'd like to embed that in the inspector view. So I can actually look at this guy. The difference is that I can lift up the playground and talk to this object and send it messages. So I can say to the, for example, if I inspect this fellow, it has, for example, a die. I say, well, I wonder what that thing is. I can just send the message self-die to that object and inspect that. Oh, and there's its die. Notice it also has a special view as well. Oh, and I can click on it. It's live. So if I click on it, the die will get rolled. Here's the Ludo game again. I have not just the board view, but I have some other views. There's a player's view. And this shows me all of the players in the system. There are 4 of them. And if I click on those, I'll get a view of the player. You notice if you are working in a traditional environment, you have just 2 views of the code. You have the running application, or you have the raw source code. But this intermediate level where you can actually talk to the objects is missing in pretty much all environments. The closest thing you can get is if you're in a web page, inspecting a web page. You open the JavaScript console, then you get an inspector view of the objects that are in that web page, and you can do some live programming things there. But you only get the raw view, essentially. You don't get these other views. Here's the list of all of the squares. And they also have dedicated views showing me where they are on the board. So what is square number 15? Oh, it's that one there. And so on. And what is player C? It has the tokens, 2 tokens, big C and little c, and they're both in the start state. So where did these views come from? You might say, okay, wow, it's nice to have these views, but they're probably super complicated to implement. Well, this is the complete implementation of that view. It's just a few lines of code. So that's the idea. You want to have the tools The tools being moldable only make sense if it's really easy and cheap to create a new view. You say, I'm looking at this object. So when I was working with the Ludo game, I say, hey, I'd like to see a list of all the players, and I'd like to see this and that. I say, oh, maybe something else. It should take me no more than a few minutes to implement a view like that. So all I do is I say, it's a view. So it's just an ordinary method that takes an argument, which is a view. The view is a view is a factory that will create the view for me. I have a pragma. This is like an annotation in Java. Annotation that said this is a test or this is whatever. This is just an annotation that said this is a view method. So when the inspector sees the Ludo game instance, it'll look at it and see which methods are defining views and say, oh, these are important methods. It's exactly the same as a test runner in Java. When you have a test runner in Java with JUnit, the test runner looks at the class and it sees which methods are tests. It says, oh, these are special methods. These are going to be the test suite that I can run. So annotations are pieces of information that you put in methods to inform tools of the IDE. That's independent of any language. So in Java you have that. You have it in other development environments. How the annotations work depends. But in Smalltalk it's exactly the same. So this is just an annotation, and it tells not the test runner but the object inspector, this is a view. So to define a new view, I just create a view method and give it this annotation. The name of the method is completely irrelevant. We have a convention for doing that, but it doesn't matter what it is. And then I say to the view, give me a columned list view. And it has this title, this priority. The priority tells you what order the views appear in. What are the items in the view? Well, the items are my players. There are 4 players. And what are the columns? So I have a player column, a token column, a state column, and so on. For each column, I say what's in there, and that's it. Easy peasy. So defining this view is super simple. Defining this view was also pretty simple. It's also a similar kind. It was also a columned list. Sorry, there we go. This one was more complicated. It's an explicit view because I actually had to spend some time to design a little user interface. But once I had that user interface, I could just plug it in as a view. I could reuse it because I have this one rendering tree. Any object I can use, I can reuse it in another context. So it's done. I didn't have to design that again. I already had it. So because I already had it, I just said, oh, well, plug it in. Oh, let's make it scalable so it'll actually fit into this space here. So by scalable, like if I make the space smaller, it'll shrink. That's just because I sent it the message as scalable so that it can zoom in and out. So if you look at all of these view methods, most of them are super simple and super small. Now, once you get this, you can start navigating through the system in interesting ways. So here I can go to the meta view, and I can see what references I have to this class. And I can see, for example, oh, I have examples. And what is this examples thing? Now, I'm not sure if I mentioned it already. What are examples? Examples are tests that also return an object. So I have a whole bunch of tests here. So here's an empty game test. What it does, it'll create a new empty game, and then it has a bunch of assertions. This looks pretty much like a test, right? So just like a unit test, it has a method name, it has an annotation saying that it's a test, in this case an example. I create the object that I'm testing, it's like a setup method, and then I have a bunch of assertions. The only thing that's different, one little thing, is I return that object. Why is that cool? If I have a green test in Java, I have a green test, so what? It's green. That's all that it gives me. If it's red, then it's useful. Then I can start debugging. Then I know there's a problem somewhere and I can use it. But once I have a green test, it's useless to me. I can look at the code, but that's it. Now, what if this tested object that I know passes all these assertions is available to me? Then I can dive into it. So now I can do something I couldn't do before. I can run this test and I can get the object and I can start looking at it and exploring it. Well, what is an NT game and what's in there? Now it becomes interesting, and I can take that and embed it in documentation. So I can reuse this thing. Now what's cool is I can compose these examples. So here's another test that takes an empty game, rolls the die once, and checks some other things, and returns a new example. So here's an empty game after which a die has been rolled, and I have a 6. And I have that object in front of me. And now I can use this guy again, reuse it in yet another one. So I take a game in which the die has been rolled 6, and I can now move the token A, and I can test some things. So here the die has been rolled and A has entered the game. And now I see more interesting things. The state of the game has changed. And I can do this on and on. Now, suppose somewhere along the line there's an error. Like this. This is going to be wrong, so there's a mistake here. But now, what's interesting, if I run all the tests, see what's happened? That's interesting. This guy was broken. That would have broken a whole bunch of other tests in a traditional unit testing framework. But now there's only one that failed, and all the others I didn't run them because they depend on this broken guy. So one, you can reuse the tests, you can reuse the examples and compose them. But second of all, if something breaks, it breaks at the lowest level and all the others don't get run. So you know immediately where the problem is. I look at this diagram and I say, here's the problem. I don't have to look at these other tests because they don't give me anything. Now if I fix this and run it, it should be fine. Let me run it over here. What's cool is I can have multiple views at the same time. Why doesn't it show me everything green? Yeah, this was not updating correctly. Okay. Yeah, so that was a very quick introduction to the examples and the fact that we can mold these views. So this means that now I have another way of looking at my application. The traditional way, I have the final running application or I have source code. Now I have in between all these interesting objects and their states, and I can explore them without having to stare at source code. Let's go. Now, let's have a look at what we can do. I said it's a live programming environment. Suppose we want to change the system. So let's take an instance of a Ludo game, and I would actually like to have a feature where I can have the game play automatically without me having to explicitly roll the die. So for example, I can, so this is the game, I can roll the die and I can move a player. And yeah, I made an error because I tried to roll twice. And now what I can do is I could try and automate a single move. So how do I know if I can roll the die? Well, I know if the player is allowed to roll. So I can see that in the player to roll method. So I keep track of what the state of the object is. There's a little bit of exploration that would have to be done, but I would learn very quickly, okay, I can roll the die if I'm in this particular state. So if I'm allowed to roll, then I'll roll the die. If I try it again, it won't work. And the other state I can be in is that the player is allowed to move. And then I can move that token, so I can run that. So I could go back and forth between these two operations, do a random die roll, and pick a player to move, if possible. And now I can combine these two as a single method. I check to the game. Is there a player that can roll? Can the player roll a die? If true, then I will get my die and I will roll it. If the player can move, then I will move the current token at random. I pick one at random of the ones that I can. So now I can run this. And whenever somebody gets a 6 and can actually move, then we keep going. And now what I can do is I can extract this. So I have an extract method refactoring. So this is, you will find that also in your Java environment. When you have a bit of code that you find would be nice to extract as a method, then you can select that code and say extract method, and it will create a new method for you. I've actually already, and then it will allow me to propose a name for it. I've actually already done that, called it autoplay, and this is it will generate for me a method like this. And now what I can do is I can say self autoplay. Run that over and over again, or I can just run it 100 times and another 100 times. Okay, and finally player B has won. If I try to continue to run, it won't, because the game is over. So now I can see what the state of all of the squares are and say, okay. So what's cool is I had this running instance of the Ludo game. I don't have to guess what code I want to write. I can actually write some code and try it out and see what works. And once I have the code that I like, then I extract it as a method. Normally what you would do in a conventional language, you would say, oh, I'd like to have an autoplay method. Let's design it. So you go and scribble on the paper, and then you start coding something, and then you or write a test case and plug it in, and then try and run it. You see it's not working. You try and debug it, and so on, until you finally get it working. Here it's the other way around. I start with an example object. I experiment with it. I say, okay, here's some code that will do this bit. I want to check if I can roll the die. And here's a bit more code that's working. Finally, I have the code that I like. Say, okay, that's what I need. Now I'll extract it as a method. Now I can write my test case that will correspond exactly to what's happening here. And then you're growing the code up starting from the example rather than the other way around. So it's a different experience. Notice here I'm always working with this view. I'm working with the playground, with the notebook, and with the playgrounds. Whereas if I were programming normally, I would be over here, and I would be trying to write this method and be trying over and over, and yeah, it's not quite doing what I want. And I'd be trying over and over again and iterating here, and slowly, maybe eventually getting to the right answer. And here, the entire process is reversed. This essentially I've told you about. So this is the story of the test methods. So here we have an empty game, and we've seen that the empty game gets used in others. So here's something that's also very nice for navigating. You can ask a method for its implementations or for its senders. So here I see that empty game is used in 2 other methods, just with a single click here. So I can see player A rolls 6, uses empty game, and game showing all moves is also using empty game. And then this is going to be used in something else, and so on. Sorry, senders, yeah. And we can see the whole hierarchy as we did before of all of these examples. The next thing that I wanted to look at very quickly, what we have now is we have the autoplay, but we can't go over the history of what the moves were. We've lost the moves in time. What would be super interesting is after playing a game, if we could go back and see what were all of these moves. So we had an original implementation of the Ludo game. That was this guy. And what we want now is a subclass, which is the Ludo. Oh, sorry, I'm in the wrong place. I want the model. Ludo game. So there's the Ludo game. And now I want a subclass of this which will record the moves. And suddenly we realize that something in our original design needs to be changed. And that's the fact that a move now should be a first-class entity. So before, we didn't have a concept of a move as an object. The moment you say, oh, moves are interesting, we want the history of moves, then we redesign the game and make a move a first-class object. Then we can inspect it, and we can keep a list, a recorded list of them. And also, each individual state of the game becomes interesting, and we want to be able to walk through. So first, we had a mutable design of the game. The mutable design of the game said a game is an entity with a state, and when I take a move, it will change the state of the game. And now we say, well, we actually are interested in the history. So this suggests we want a different design of the Ludo game in which the game is immutable. When I make a move, I get a new instance of the game, so it becomes like a state machine. So before, I had a Ludo game, and I roll the die, or I move, and the state gets updated. Now, I have a new design, and say this is the state, the empty state, and then I roll the die, and I get a new state in which the die has been rolled, and then I maybe have a move, and I get yet another state, and so on. I really get a state machine. And each of these states is now completely immutable. And you might say, oh God, we have to redesign the whole game. In fact, you don't have to. It turns out that we can just inherit from the existing Ludo game. We change a few methods, and we change the logic of just those methods which assume that the Ludo game is mutable, and instead have them do different things. So now a move becomes a first-class thing, and the state of the game, every time I make a move, instead of updating myself, I get a new Ludo game. And that's what we're trying to do here. So here's an example of GT Ludo recording game examples. We have and this is now a subclass of the other examples as well. So we have all the old tests, and now we have some new ones. So here we have a Ludo game, and actually I've taken this autoplay thingy and turned it into an action. So now I can just click on this. So notice each time I click on this, I'm updating and I'm getting a new state. And I'm also inspecting now the move. I can also autoplay 10 times. And when I inspect this guy, there are some new views. I have the list of the moves so far. And I have a history view. So the history view is basically these guys. So these are the Ludo moves. And each move, I'm reusing the visual display that I had before, but now I'm showing what actually happened in the move. So now I can go back in the history of the game and see that player A rolled a 6, and then a token got into the game, another token got in, small a moved forward, another 6, and so on. And at some point, player B wants to get in, but he doesn't manage to roll, and we keep going forward in time. We could play 100 times and go much further forward, and we see here eventually player D managed to roll a 6 and get into the game. By changing the design so that we have an immutable rather than an immutable game, we get for free the fact that we can browse through the history. We have to do a little bit of work to get these new views, but that's pretty straightforward. And now, almost for free, we get kind of a back-in-time ability to play through the game and browse through the history, just by having these views next to each other. So I'm not doing anything explicitly in terms of animation, but I actually get kind of an animated view of the game being played. The other thing that I can do, which is kind of nice, is I can replay the game to a certain point, and now I have a new game, a new instance of the Ludo game that stopped at move number 41, and now at this stage we can let the game take a different route from here. We could explicitly try different kinds of moves just to see what would happen, or we could simply continue executing from that stage. And here in this one, oh, player A1 there and player A1 there as well. But it could just as well have been another player that might have won in a different path of the execution of the game. Once you have all this stuff, you can actually use these live examples to build some documentation. So we have test cases. Before, if you have a test case that's green, it's just green. But the test cases are documenting interesting things that could happen. Particularly one that I like is the impossible move. So the impossible move here, B, is near the end of the game, but he rolls a 6. So it goes 1, 2, 3, 4, 5, 6, he can't go, so he ends up going back, and he's not able to make any move because he rolled a number that was too high, even though he's near the end. So once you have these examples, you can also embed them into your documentation, and then you get for free reuse of the tests as examples that illustrate interesting things in your application. You can also do other things, like here, for example, we have UML documentation of the whole implementation, but I would argue this is terrible, right? Like, you can't read that, can you? I mean, it's live, and I can click on things, but it's completely unreadable. So this is one thing you should watch out for. Generated UML is typically useless. What you want with UML is you want to design a UML diagram so it's highlighting things that are of interest to you. So having UML that just shows you everything is rarely useful. Instead, what you could do, you can say, okay, I just want to have the model classes. That's already a little bit better. So if I go to my package here, I see that the implementation of the Ludo game is the Ludo game package, is broken up into several sub-packages. So I have the model classes, I have the user interface classes, I have the examples or tests, I have the announcements which are used for the model view controller. So when something happens in the model, I have to inform the view. Those are the events that get raised to keep the model and the view in sync. And some specialized exceptions. So if I'm interested in the underlying model, I just want to see those classes. So that's exactly what I've done here. So I've taken a smaller UML diagram, but there's still way too much noise here because I don't need the list of all of these methods. So I could still generate yet another UML diagram, for example, like this one is already much more useful. It's showing me, here's the original design of the game, the Ludo game, and the Ludo game has a die. We have players and tokens, and the players and tokens are live entities, are named entities. Notice what's also cool is that the UML diagram is linked to the whole IDE, so I can directly navigate. It's not just a dead picture. I can actually navigate here to the source code. And I can see that here at the top is the original implementation, and when I made the recording game, it's a subclass of game, and I've introduced something completely new, which is the move entity, in order to turn that into an object, whereas before it was just something that happened. So already that's something much more useful as a UML diagram, because you've designed it to only highlight things which are of interest, and ignoring the things which are just noise. That was everything that I wanted to tell you, but I wanted to leave some time for questions and answers. There are many more things that I can show you, so I encourage you to ask, and also encourage you to try out the system. So what are the key messages? One is live programming. Second message is about the examples. So examples are composable tests. By the way, if you're at all interested in this, we implemented a Java version of this called JExample. And if you just Google for it, you will find the implementation still works. So there are lots of examples, and you can download it for Java and actually play with it. So this is not something, the main message is the concept of tests returning example objects is not something specific to Smalltalk. You can implement it really easily for any other programming language where you have a unit testing framework. And then the third thing that I want you to remember is this idea of moldable development. The fact that when you're developing in such an environment, you can actually open up your development tools and make them moldable so that they tell you more about your specific application domain. So you're actually changing the development tools so that they can answer interesting questions about your domain objects. Just like with the Ludo game, we had all these additional views which allowed us to dive into an actual running Ludo game and explore what's going on instead of just having the end user interface or just the source code. Final slide then. As I said, this is all open source. You can download it from gtoolkit.com. It should run on your platform. There's a book built into the system itself, which I just showed you very briefly. And there are actually more conventional books available as well. There's also a Discord community. So if you start playing with it and have questions from the gtoolkit page, you will find a link to the Discord server for GT, and people are happy to answer your questions. Good. Thanks for listening. That was what I wanted to show you so far, but as I said, I'm happy to answer more questions or show you other things if you're interested. Thank you. Yes?
Well, you showed us several of things that Smalltalk can do quite easily that are much harder to implement in other languages. But more specifically, which kind of situation, so the type of application, the entire development process around it, would you actually recommend the use of Smalltalk over a more conventional language like C++ or Java?
I'm reminded of this this gag about somebody saying, I recommend using testing only for projects that you would like to succeed. And I kind of feel the same way about Smalltalk. So if you, I think for a lot of kinds of applications, if you're free in the choice of the technology, it brings a lot of advantages. Sometimes you're locked into a certain technology, but then you can use Smalltalk as a bridge. So for example, with Timo, we have this student who's looking at GitHub Actions. And what we're doing is we're using GT to build up an explorable model of the GitHub Actions so that we can understand better what's happening there. So typically what you want to do is if you have another programming language or system or data, you load that into GT so you can build a kind of a model, or I hesitate to use the word digital twin, but it's kind of like that. What you want to do is you want to build an explorable model of whatever the domain is. We also have bridges to other languages like Python and Ruby, and sometimes to Java, so we can do certain things with other programming environments when we need so for our customers. So to some extent, we're kind of customer-driven in terms of what bridges we can build to other environments. But that's certainly doable. One of the downsides with Smalltalk is being stuck in the image. So if I want to collaborate with you, we maybe have a Zoom session together, and one of us will have GT running. And with Zoom, I can maybe control your keyboard or whatever, but we can't have two images that are synced at the moment. That would be doable too, but it's not there. But frankly, with most other programming environments, you don't have that either. But that's a bit of a limitation. We'd really like to get to the point where you have something which goes beyond a single Smalltalk image. If you want to do things with concurrency, here we're not exploiting multiple CPUs. So we have just one CPU at a time. So you'd need multiple images running. We do that, for example, with Lifeware because they have thousands of tests that they need to run. So we run them on AWS using hundreds of nodes, which are each running a GT image. And these are all then controlled and synchronized from another one so that we can see what's happening. So those things you can do as well. But all that infrastructure has to be built up. Nothing's for free. But I guess that would be the same. That's the same case with any other technology you might pick. I don't know if I answered your question. I'll let you think about it if you want to ask it a different way. Yes?
I mean, the one implementation that I can see right now is just, I have an idea, I want to develop it a bit, test it, see how it goes for a program, and then, because it's so easy to do it in the Smalltalk, then like develop it and deploy it or do whatever with another programming language.
Mm-hmm.
But like my question is, it's a bit so GUI heavy, let's say. It's a bit like click-bitty. I have to click everywhere. It's not like conventional programming.
Actually, you may not have noticed this, and in fact, when I start working with, if I do a session together with people, very often they say, oh, now I have to do something over there, and they want to open up the coder tool, and they want to open up another tool. I say, wait. You don't need to click around. You can actually just stay within the same workflow. So I was trying to do that there. So you saw very often I'm starting from a notebook page, inspecting an object, going to another one, and then going back. I tried to stay within the same flow instead of opening a new window on another thing. So this whole flow going back and forth allows you to stay within the same framework. It's really very different way of working.
And it's completely different. It's also like in those views, it's most like widgets, let's say.
Mm-hmm.
And I don't know, the kind of version I get, it's very simple, but yet it's like very tricky to, like, you obviously understand much more that you can work and talk about it, but like for somebody like me, I say it, or I can compare it to something like, let's say, low code development, although like underneath it's much, let's say, complicated stuff that's going on.
Mm-hmm.
But I see it like more as like, let's say, yeah, I don't know.
Yeah, it takes a little bit of time to get used to it. One thing that is fundamentally different is in almost all programming environments when you do what is called object-oriented programming. In fact, you're not. You're doing class-oriented programming. You program a class, then you compile that and run that, and then you have objects. But what you're working with is not the objects. Whereas here, when you start, you try to get a running example as quickly as possible. You can talk to that object and test out code. That's object-oriented programming. You're actually working with live objects and experimenting and trying out different bits of code until you can get examples and start writing your tests and developing further. But you're always working with something live. It's also a different way of thinking, and it takes a little bit of time getting used to it. I had the same experience when I started working with GT. I was in the coder a lot of the time, and I was writing tests first and so on. And then it took me a while to realize that, hey, I can actually do this from the inspector. Here's one of the things. So one of the things that I did quite early on was writing these slideshows. So writing the slideshow, a slideshow is just a class. So I started programming the slideshows by writing these methods. And at a certain point it hit me. I said, oh, this moldable development environment, I shouldn't be treating the slideshow as a class. I should be treating it as an object. And once I realized that, I started creating these views. And I said, okay, the first thing I do when I get a slideshow is I get an instance of it. So let's inspect it. And Here I'm inspecting the slideshow. And here's a slide. And the slide is a method, but I want different views on it. I want the live view of the slide. I want the slide with the text. I want the slides in order with the priorities. I'd like the slide deck showing me all of the slides with the annotations together. So all of these different views. And now that I have that, and even some metrics that I generate. So given the text that I've designed, how long do I expect the slideshow to last? So now I can ask interesting questions about the slideshow. When I had just the methods view, I was stuck in the view that a typical IDE would give you. And I just see the methods in the source code. I can't do anything with it. Now that I have the live object, I can inspect it, I can run it, I can inspect an individual slide and run that and open it up in a window and play with it. And I can really incrementally and experimentally develop the slideshow in a much more comfortable way. The funny thing was, I'd been working with it for about a year before I realized, oh, I'm doing this wrong. And it took me literally just a couple of hours to add all these views, and it changed the way I worked with it. But it takes some time to realize that, that it's a different way of thinking. And it's the same no matter what you're developing. Any kind of application that we've experienced, you can really do it in a very different way. Any more, maybe more down-to-earth questions? I mean, I'm getting very mystical and and philosophical here. Yeah.
I do not understand how everything can be an object. I mean, for example, the object true, that leads to something that is not an object. Or is it only implemented with bytecode and then we use the object true? Or how does it work?
Well, true is an instance of the class true. False is an instance of the class false. And they each have their own implementations. So if I go to the class Boolean, I see that it has two subclasses. It has the method and this is an abstract method. So if a Boolean and another Boolean, the result, I don't know what it is because I don't know what Boolean is. But if I go to the two subclass implementation, the implementation of and for true is to return the other Boolean. The implementation of and for false is to return myself. So false and anything is always false. True and anything else is whatever that other thing is. So they're just two different implementations of and. So you exploit the class hierarchy to give different behaviors to these Booleans. And aside from that, a Boolean instance, true, is just an object. And I can inspect it. There's the object. The raw view, it's just true, what it is. And there's not much more to say about it. It's like a single, a unary value. It's just a plain value with behavior associated with it. The trick is, here I have the impression that it's a real object. In actual fact, when you compile the bytecode and you see true or false in order to make things run fast, true and false get compiled away at some point. But for all intents and purposes, they are real live objects. And you can tell that because I can add new methods to the class Boolean or true or false, and those new methods will work for Booleans once I add them. But I can't change the underlying implementation of true and false or add new instance variables or things because that would break the compiler and so on. At a certain point, you hit the limits of what you can change, but you can change many, many things. Yeah?
So here, at least by default, do we have the objects of true and false? Are those singletons of the class true and false, or do we always create new instances of true and false?
They're special. So also if I say true new, you can't have any more Booleans. You can't do that. And also, because it's a pure value. And if I also say small integer new, that also doesn't make any sense. So some things at a low level don't make any sense. But for all intents and purposes, they really behave like objects up into a low level. And until a certain point, the illusion breaks. But you have to go really deep before you realize, okay, everything's an object, but true and false are kind of a little special, and integer 1 is a little bit special, and so on. But the illusion goes down very, very deep. Much more, though, than it does in most other programming languages. And it works well. As I said, if you want to extend these classes with new methods, that works beautifully. I can define new methods for integers and numbers and so on. And that works well. Anything else? Okay, then I guess gone a little bit over time. Time for a break, and you have an exercise hour. If anybody's interested to follow this up, I'm available online, so you can find me. Best way is through Discord. So there's an active community there. So if you have questions and so on, it's a good place to ask. Thanks for your attention.